Hello students, welcome to the next lecture on the probability and stat. Today we will discuss about mathematical expectations and its property of the random variables. Myself, Dr. Garg, working in the School of Mathematics, Thapar Institute, India. You can contact me either of my email IDs if you feel any doubt in this probability and stat. So now we will define what is the mathematical expectation. So in the probability theory, mathematical expectation is also called as the average expectations, mean, as well as the first movement here, and it is a generalization of the weighted average. We all know in your lower classes you have read about this mean, that is a summation of the fx by f. But now here we will replace this probability to this frequency to the probability, or informally this is nothing but the arithmetic means of the large number which are selected independently from the outcomes of the random variable. In most of the cases, or you can say the expected value is denoted by capital E, and if you have the random variable x, then the expected value of the random variable is denoted by this. Now depending upon the nature of this x, whether it's a discrete or continuous, we can define the expected values like of here. So when you have the discrete random variable, then we can define as a summation of x into px, where px is nothing but the probability mass function. If you have the continuous random variable, then it is the integration of the domain, like say from minus infinity to plus infinity, where fx is pdf. Make sure that this is, if you define like say x square, this is expected value of the x square, then we have to write this as a x square and p of x. So whatever the thing you have written here, the same will be written like here. For example, if I write here as say y, then it will be nothing but my y and the PMF of the y's. Now since this is the summation from minus infinity to plus infinity, and this is again here, so this expected value exists provided when this series is convergent, as well as this integration is absolutely convergent. What is the meaning of the absolutely convergent? Is that means that is this series, that is the modulus of this is a finite value and this is a finite value. Why we call as the absolute convergence? So because we all know the absolute convergence implies the ordinary convergence. So it means whenever this condition holds, it means the expected values of the given series will exist. This is one of the most important result, is the expected value is exist only when expected value of the modulus of the x exists. There are so many examples that in which this value does not exist because of here. So look at the first example. If you consider the random variable x, which have considered only the values as a 0 factorial, 1 factorial and 2 factorial and so on. In general, it will be x factorial when x will by 0, 1, 2 and so on. And the corresponding probability is by here. Now you can clearly say that this is my PMF, because if you take this value, what will happen? 1 by e is outside, it is 1 by x factorial. What is the 1 by x factorial? It is nothing but my e raised to power 1. It is a 1. So what is the meaning of that? This is nothing but my PMF. Then if you find the value of this e of x factorial, that is here, if you substitute the value of the x here, x factorial will be cancelled out, so it will be 1 by e. What is the 1 by e? It's a constant value, so 1 by e of outside. What is the here? What is the summation of this? That will goes to the infinite because of the divergent series. So since this series is divergent, it means expected value does not exist. On the other hand, if you consider another example like of this, if I consider the random variable which takes this value and the respective probabilities are here, again you can easily verify that the values of this probability of the xi is nothing but my 1. Then we can define the expected value, that's x into px. So if I multiply them, then this value will be cancelled out here. Do you think that what is that? Is the series convergent? What kind of the series is here? Yes, this is the alternating series. So once it is an alternating series, which test you can apply? That is nothing but my Leibniz test is there. Now you can clearly see that with the help of the Leibniz test, this series is convergent. Why? Because the 1 by this is my here, it is a decreasing sequence and it approaches to the 0 as n approaches infinity. So clearly says that in this case, instead of the n is I. So clearly says that whenever I goes to the infinity, it's therefore by using the Leibniz test, this is a convergent. So once it's a convergent, you can find the sum. How you can find the sum? If you put I as a 1, it will be 1 upon 1, then 1 by 2 plus 1 by 3 minus 1 by 4 and so on. So do you remember that? What is the sum of this? This is nothing but my log of 2 is there. You can see the sum is my finite. It means that existence is there, but that is not true. For existence, you have to check whether this is there or not. What is the mode of xi? So this is my xi, this value is my 1, so it will be nothing but my here, because what is the mode of xi? Mode of xi is nothing but my I plus 1. So if you multiply this I plus 1 of p, you will get this. Clearly says that, what is that? This series is my divergent by using the p test, because p is my less than equal to 1, then it's a divergent. So it clearly says it does not converges, therefore expected value of this random variable does not exist, although this is a finite. Look at the another example. Again you can see I taken this as a random variable and the corresponding probability is here. So if we start with this exercise, again you can see this is a alternating series which is a convergent, and you can see the sum is my minus of 2. But if you find the expected value of the mode of x, what is the mode of x? It will be this value is my plus 1, so that is my 2 raised to power k of k into probability is my here. Again you will get this series as 1 by k. K varies from 1 to infinity. What is that? This is again a divergent series by using the p test. So therefore this is a divergent series, hence expected value of this does not exist, although it has a finite value. Look at the another one is there. So if you consider the random variable x, this is my continuous random variable and it is a well-known PDF of the Cauchy distribution. Then in order to define whether the mathematical expectation exists, we can start with the mode of x. So what is that? This function, whenever it's from minus infinity to infinity, this is my even function, so we can write this as twice from 0 to infinity. So we can write like of this. So what is the integration of this? I can take 1 plus x square as nothing but y, then 2x dx is nothing but dy. So what is that? This is nothing but my log of 1 plus x square over 0 to infinity. So what is that? Whenever it's a infinity, it goes to the infinity. So that means this is the divergent series, hence this integration is not convergent, therefore the expected value does not exist. Now what are the properties of the mathematical expectations? So there are so many properties are there. The first one is a very important one. So if you consider x is any random variable, either it's a discrete or continuous, and a is my constant number, then this expected value is here provided all the expected values exist, where phi is nothing but any function of the x. So we can start with the definition of this. Since it is if I consider as a continuous random variable, then you have to take the integration. Since this is my constant, so I can take this outside. What is that? This is nothing but the expected value of this. So the first part is simply proof. Similarly, we can prove the second part. We can start with the expected value of this, that is nothing but my here of fx. Now I can take this as separate. It can be written as phi x of this plus from minus infinity to infinity a of fx dx. So what is that? This is nothing but expected value of phi x. This is a is outside. So what is the minus infinity to plus infinity fx of dx? So since this value is my 1, why? Because fx is my PDF. So once is a PDF, so the total area is my 1. So you will get the required answer and this required proof. Here the most important thing is what is the nature of this phi x. So why phi x is a function of the x, can it be the linear or non-linear? So the major question is, if you consider the phi x is my simply x, so this is nothing but my ax. So therefore expected value of the ax is nothing but a times the expected value of x, and expected value of the x plus a is nothing but my here. So from here you can also see what is the expected value of the ax plus of say by. You can easily write this as ax, or you can simply say, if I consider this value as here, then this is nothing but my, this is the result. Also, if you consider the phi x as my 1, if you substitute here as a phi x is 1, what is that? Expected value of the a is nothing but my here. That means expected values of 5, that is nothing but my 5. expected value of the minus 7 is nothing but my minus 7. Another thing is, if you consider the phi x is my linear, like of ax plus b, then the expected value is nothing but the linear function of the expected value. Proof is very simple. We can start from the left hand side. This is my left hand side. So if you start from here, now by using the previous result, we can write this value as here. What is that? This is nothing but my, I can replace x with the e of x. That is nothing but my, this result is nothing but my phi of ex. Now it should be noted that here the phi is must be the linear. If phi is my non-linear, then this result is not true. Like if phi is my non-linear, then this is not true as of this. Meaning, for example, here we can see 1 by x is a non-linear, then it is not equal to the 1 by ex. E of x square is not equal to e of x whole square, and so on. So whenever this is a non-linear, then this equality does not hold. We can consider the one example. If I consider x is my random variable, which consists of only two values, -1 and 1, and the corresponding probability is my half and half, then what is the value of the ex? If I start from the ex, that is nothing but my half minus half of this, half and 1 by 2, that's 0. What is the expected value of the x square? X square, that's a -1 square of 1 by 2, 1 square of 1 by 2, it comes to be 1. Clearly says that e of x square is not equal to e of x whole square, like of this. Similarly, you can define like this way, it is not be true. So therefore this is true. So now if you want to find the relation between them, that is the discuss about the Jensen equality, which is we already discussed in our previous lecture. You can see on the I button link out. So the only relation between them, whether since it's not equal to, so either it can be greater than equal to or it can be less than equal to, that is defined by the Jensen inequality. Another properties are there. Whenever x is my positive random variable, then expected value is always the positive, and whenever this is, what is the meaning of that? Expected value is the increasing function. So the simple thing is that if I consider x is my continuous random variable, then what is the meaning of this? X is greater than 0, then here. If you consider this as my discrete, then you have to replace this as of here. Now since x is my greater than 0, so this integration is nothing but my from 0 to infinity here. Here you can see x is my positive number, f of x is my, what is the f of x is my PDF. What is the PDF nature? Is always be greater than 0. This number is also be greater than 0. The product is also greater than 0. So therefore the answer is my greater than 0, provided this integration exists. Same proof we can do for here. What is given to you? Y is less than x, it means x minus y greater than 0. So when anything is greater than 0, what is the meaning of that? X minus y is greater than 0. So I can write this number as ex minus ey, which is greater than 0. So therefore ex is my greater than of ey, provided expected value of the x and y both are existence is there. Look about the another property. So the absolute value of the expected value is always be less than of this, because you all know that mod x is a non-linear. So once it's a non-linear, it can never be the equality sign. The proof is very simple. We all know that x is less than of the mod x. So by using this result, whenever y is less than of this, that is, what is the meaning of that? Expected value is a increasing function. So now we can apply the same result here. Further, we all know that minus of x is also be less than of the mod x. Again we can apply here, this will be here. So from 1 and 2, what is the meaning of the from 1 and 2? Can I say the left hand side is nothing but my mod of fx, mod of the ex, and it will be here. Another method, this is a second proof. How you can prove that? Again, let's consider x is my, say, discrete in this case. If x is my discrete random variable, then we can define the expected value of here. We can start with a mod. So what is the mod of this? So we all know what is the mod of this. It is less than or equal to expected value of this. So I can write this value, expected value, summation is outside of this. Now what is the p of x? Px is my probability mass function, which is always be greater than 0. So I can write this number as mod x of px. What is that? this is nothing but expected value of mod x. So this means mod of expected value is less than or equal to expected values of. This is the required proof of this result. Another result is, so if you prove that expected value of some r exists, then expected value of all those s which are less than of the r are always exist r. What is the meaning of the expected value of xr exists? Means integration from minus infinity to plus infinity is less than here. Now we can start with the expected value of here. So in order to existence of them, we will try to start from the mode of this. This is the definition. Now we can discretize this over the two integration. One is from -1 to 1 and other from here. What about this one? So whenever x is lies between -1 to +1, what is the mode of this? This is always be less than of the 1. So it means this number is always be less than of the 1. On the other hand, whenever x is greater than 1 and then whenever s is less than of the r, what is the meaning of that? Mode of the s is always be less than of the mode of this for x is greater than 1. So whenever x is here, whenever x is greater than 1, say let's say 2 raised to power is so. So therefore this number is my less than 1. I can write this number is my less than 1 here, plus this is my mode of x is greater than, this number is less than of r fx dx. Now what is that? This is my PDF. Now since this is my here, so this is always, this number we all know this number is my 1. So from -1 to 1 is always be less than 1, and from here we can see this number is my finite. So what is that? This is number is nothing but my mode of here, so which is nothing but my finite. Therefore expected value of modulus is finite. It means expected value of this is existence in nature. Similarly, we can prove that expected value of the sum is nothing but the sum of the expected value. That's again very simple. If you consider the x and y are the two random variables, say continuous, and the PDF is my fx and dy, and fxy is my joint PDF, then we can define here for the continuous random variable steps. If you have the discrete random variable, then you have to write this number for x and y as here. Now I can open this bracket for the two sides. What is that? This is with respect to x, so I can consider this part x is outside of this. What is that? This is nothing but my marginal density function of y. This is the marginal density function of y, this is the marginal density function of the x. So what is the marginal density function of x? Is fx. This is nothing but my fy. So what is that? X into fx is nothing but the expected value of x. This is expected value of y provided expected existence is there. So this result, that is for the two variables, we can extend them to the n variables are. Same result we can do for the multiplication. So there is a multiplication theorem. If you have this independent random variable, then product is equal to this. But make sure that whenever x and y are independent, then only you can write this as product. But they are not equal if x and y are not independent. This is one of the most important results. So again we can start with a continuous random variable. We can start from here. What is the meaning of the independencies? That is the fxy is nothing but my here. So we can subtract from the left hand side. We can write here. We can substitute this value as fx fy, and then I can take the pairs with respect to x separately with respect to y here. This number is my fx. This is my fy is the required proof. Again we can extend the same thing to the n independent events. That is the product of this for the n independent, then only you can write like here. How you can find the expected value of the function of the random variables? What is the meaning of that? If you consider g is the any function such that g of x is my random variable, how you can define the expected value of the gx? Like here, if it is a discrete, so as I told you, whatever you have written here, that is nothing but here. Similarly, this value is nothing but here, provided expectations, provided this summation and this integration converges absolutely. Same result for here. If you have the independent random variable, then the expected value of the function of the x, expected value of the function of y is nothing but the expected values are here. Proof is again very simple. The same way we can start, because of the independence we can write like this way. We can start from the left hand side. We can substitute the value of this as of here. Now what is the meaning of that? Because expected value of this is existence, so it means the integral on this value is absolutely convergent. Once this is absolutely convergent, then we can change the order of the integration by using the Fibonacci theorem. That is, we can consider the pair of the x with respect to the dx, and here what is that? This is nothing but expected value of this is the expected value of y is my here. So this is the way you can think about this expectation of the random variable. That's all about this today's lecture. We will see in the next lectures with some more properties about this expectation. I hope you can simply like, share and comment on this video and share with your friends. Best of luck students. Happy learning.